you generally use the quadratic formula, right? And the kinds of solutions you can get depend on what's under the radical, right? When the thing under the radical is negative, you get imaginary or complex. One, you can have two complex solutions. Okay. When the number under the radical is positive, you get two real solutions. And when the number under the radical is 0, you get one repeated solution. Yep. One real repeated solution. Right? If I plugged into the quadratic formula and it was like it's negative b plus or minus the square root b squared minus 4ac all over 2a. If what was under the radical was 0, you'd still have a solution. It would just be negative b plus or minus 0 over 2a. And when you add 0 or subtract 0, you get the same number. For the last one, 1 root, that's fine. And 2, no, it needs to say real. You can get like, so give yourself, yeah, you can give yourself 1 point for the first two for writing 2 roots. So you get 2 out of 3 there. Okay. When you're finding eigenvalues for a system, you always end up solving a quadratic, right? You find the characteristic polynomial by doing the determinant of a minus lambda I. It always turns into a quadratic when you're dealing with a 2 by 2 matrix. So today we're going to talk about what happens if you only have one eigenvalue. So in previous classes, we talked about what happens when you get 2 real eigenvalues. We've done that. We've done 2 complex solutions, 2 complex eigenvalues. And now we're going to talk about what do you get when you do 1 repeated solution. And it turns out that the single repeated 0 is like a boundary. It's like, so this blue graph here, it's a quadratic function. It's got 2 real zeros. And as you move it up, there's a moment where it has 1 repeated 0. And then after that, it has 2 complex solutions, no real zeros. So this red graph is like the boundary between 2 real solutions and 2 complex solutions. So it's going to have some characteristics of both 2 real eigenvalues and 2 complex eigenvalues. Forms the boundary. Okay, so similarly, the case of single repeated eigenvalues form a boundary between systems that behave like those with 2 real eigenvalues and those with 2 complex eigenvalues. So it's sort of in between. All right, so here's a system. I want to compute its eigenvalues. So remember, you compute eigenvalues by taking the determinant of a minus lambda I, setting it equal to 0. This guy is a, and lambda I is just lambda 0, 0, lambda, subtract component-wise. So I have negative 2 minus lambda, 1, 0, and negative 2 minus lambda. And I'm going to take the determinant of that, set it equal to 0. And you take the determinant by multiplying those guys. So I'm going to have negative 2 minus lambda times negative 2 minus lambda minus 0 equals 0. So it turns out that lambda is going to be negative 2. And that's the only eigenvalue, one eigenvalue of negative 2 when you solve that. Okay. So I do have one eigenvalue, one real eigenvalue, which means I can come up with a straight line solution. Remember, straight line solutions look like e to the lambda t b. And lambda is your eigenvalue, and I need the eigenvector associated with that. That's my v. So I got to come up with a v. And to find v, you solve the equation av equals lambda v. Oops. So A is -2, 1, 0, -2 times some unknown vector v equals lambda, which is -2, times the same unknown vector v. So we're looking for some vector xy that makes this true. So this says -2x plus y has to equal -2x, and -2y has to equal -2y. So this second equation is always true, no matter what y is. So I have, this is no info. So this one says that y has to equal 0. You add 2x to both sides, you get y equals 0. So what's an eigenvector with y equals 0? 1, 0. Anything as long as the 0, the second coordinate is 0. So my straight line solution is going to be y equals e to the -2t times 1, 0. Right, so far everything's the same, right? We found an eigenvalue. It turned out there happened to be only one. We can get the associated eigenvector and find a straight line solution. The problem now is that in order to find the general solution, so that's one solution, but in order to find the general solution, you need two particular solutions that you take a linear combination of. You do k1 times the first one plus k2 times the second one, and that's your general solution. But I only have one straight line solution, so I can't do that right now. I have no way of getting the general solution. But I could plot a vector field and look at its phase portrait. So here's a vector field. I followed several paths along for various different initial conditions. And it does kind of look like this was my straight line solution 1, 0, right? So that one shows up there. The eigenvalue was negative, so it all points towards the origin. And then the rest of the solutions are sort of a cross between a sink and a spiral sink. Like they're kind of like trying to spiral, but then this straight line solution gets in the way. Right, so the sink was when everything just came in towards 0 along an eigenvector. So it's very similar, but it looks swirlier than the real sink, than the straight sink, because it's the boundary between a sink and a spiral sink. All right, so all solutions tend towards the origin. We classify this fixed point as a sink. It seems like the solutions want to spiral, but the straight line solution gets in the way. The boundary between a sink and a spiral sink. All right, so I want to use this phase portrait to try to sketch the graphs of x of t and y of t solutions using the initial condition 1, 2. Right, so that means that the initial x value is 1 and the initial y value is 2. So I've got this solution plotted. That's my initial condition. So just as we follow this solution path towards the origin, what happens to the x values? They just get smaller. Yeah. So x is going to start at 1 and just decrease. So x is going to be pink. And then as I follow that same solution path towards the origin, what's happening to y's? The same thing. Yep. But the y's are starting at 2 and decreasing. Okay, so coming up with the general formula is left to you guys to do as part of the class activities. Once you have the general formula, see if it makes sense that that this picture matches what you come up with.